All right, let's continue. So we were able to actually implement a stack with a linked list approach, and we left off with something that was somewhat working, except that now, again, our code is a little messy here. So why don't we take a chance right now to actually do a little refactoring by separating out some of these functions and then possibly renaming them to be more appropriate for what we were trying to achieve here. So similar with our stack array, let's just create two new files, stack.h, and then we'll do stack.c. Okay, so let's actually split this to the right here, and let's start just defining some of our functions. So first things first is that we always do something like this. If not defined, stack h, define stack h. No, I haven't explained why we do it like this yet, but we'll get there. So I think last time we were saying that node, or at least any struct, is common amongst every piece of code that we use. So, and we're going to be including stack.h within main.c and stack.c anyway. So it might be worth it to just put that here inside our header file. Okay, and then we should just start writing the signatures for all our functions. So we can say something like this: stack node stack create node, and then we'll give it a value here as the starting point, and then we're just going to do something like this. Or actually, what am I doing? I'm implementing it again. Let's just do that. Okay. Then the next one is going to be push node push. We're going to take in a node head int value, and then we're going to check is empty. Bool is stack push. Stack is empty. Node head. Then we're going to say stack pop. And we're going to have a double pointer, because last time we said that we're going to modify the pointer here. Just removes it from the stack. Okay. Then stack peak, which is also just taking in a pointer. Then we'll have free list. How should we say? Should we just say free stack? Stack free? Stack free? Stack free? Yeah, let's just say stack free. Or stack destroy. Let's do that. Or how about stack empty? And that'll take in single node that represents the head of the stack. And then we'll have stack void stack print, which is also going to take in the head of the stack, the top of the stack, pretty much. Okay. So we're going to also need to include the std bool. So here we'll include std bool.h because we're using bool here. What else do we need? Looks like that's all we need here. Okay, so that's all our function definitions, and we can write that. And next, let's actually do some implementation. So let's actually toss this down here, and let's just start going slowly, transferring all this code from main into stack.c. first things first, it looks like we'll need some includes. So first let's include stdlib.h. Let's also include stdbool.h. And also we did do some like prints and all that stuff too, so we need stdio.h too. Okay. Finally we need to include our stack.h. Okay. And now let's just start implementing them. So this is our first function, node stack create node. And it'll be int value here. And we'll just copy all of this. Actually, just cut all of this. And just paste it here. Okay. And then we can just delete that. Okay. And then we'll actually say this as create a node ready to be placed or pushed into the stack. Okay. That's pretty descriptive enough. The next one is going to be stack push. Why are these squigglies here? Function is not found. Anyway, node stack push, and we're saying it's node head and value, and this changes basically what is going to be the head of the stack. So let's just take everything here. Take that out. Paste that there. Let's also take this too. That out. Just put that here. Pushes the value at the top side, returns a reference to the new top of the stack. To the new top of the stack. And I don't think we need this. I think we can just change this to that. Okay. And now we don't need this one anymore. Okay, now it's empty. So we'll say bool stack is empty, pointer to a node, and simple as checking to see if the head is null. Then we'll just copy this, take that, put that here, take this, returns true. You know what? Let's also do this. I don't like all these spaces. Yeah, let's also fix that up here. Okay. Okay. Looking good. So this get rid of. Next is going to be stack pop. So int stack pop double pointer. That's going to be, ooh, this is complicated code here. Okay, take that out. Paste that here. We're also going to take all this, take that out, paste that there, take that, turn this into uppercase, move some spacing. Okay, done with that. Next is going to be stack peak, which is kind of like pop, except easier. So this one, paste that there. Then we'll need the comment. Cool. Oops. Right here. Get rid of that. Okay. So this we don't need. Now we're going to have this free run right here. So we'll we're calling this one void stack empty, not free list anymore. Okay, and then we'll take all this, paste that, then we'll just say freeze allocated memory from the stack. And then we don't need any of that. Then stack print, which is our last one, it's also void stack print. And that is going to be all of this here. Get rid of that, paste, boom. Okay? Okay. Oops. Okay. So, oh, we should add a comment here. Print the contents of the stack. Great. So now let's actually fix up main, because now we're going to need another include, which is going to be stack.h, so that we can have the node pointer to a node defined. Okay, so that's as simple as stack.h. So then we'll have that defined. But then these here will be all stack push. So stack underscore push, stack underscore push. Oops. Stack underscore push, underscore push. And I think we could, actually we don't need this. Okay, and then this will be stack is empty. And this will be stack pop. And then, ooh, wait. Oh yeah, we freed it this way. Every time we free, we will, okay. But we're safe here, right? So the reason why I commented this out yesterday, or not yesterday, last time, was because as we pop, we're already freeing our elements. So here, this is the free, okay? I think it would be fine, maybe, if we kept it like this. Then, if we were popping, let's say we free prev head. Well, let's also say prev head is going to be null, just in case. As we free things, we'll set that to null. Okay. Even wait, does that matter? It's already freed. This will get blown away, but then that's the reference there too. Sure, let's just do that. Let's see what happens. So let's test it. Hello. Okay. GCC main.c stack.c. Ooh. Oh, what? Oh yeah, that's true. All this here. I'm getting errors because I forgot to fix all of this stuff here. Alright, let's do that real quick. Stack create node. Stack create node. Stack is empty. Okay, and what else do we have? Stack is empty. Then looks good. Okay, save that. Let's try again. One more. Free list. Silly me. Okay. stack empty. Okay. Now, okay, it looks like it still works. So, do we even need to do this? Let's see. Guess not. All right. I think the next thing we should do is we should probably rename. I don't really like how we call this head here. We should just rename all these to something like top because it technically communicates as the top of the stack. Oops. Okay. And then the other side, yeah, we also said these were heads, but I think it's more like top. So let's name that top. This one should be top too. And let's see what else do we have. Okay, this one should be top too. Okay, and this one top. Oh, up there too. Okay. Down here. Ooh. Okay. Squigglies. Okay. Push and pop might be like the most involved. Actually, not too much. Okay, let's do it. And this is called prev head. In this case, prev top. And then this one should be prev top now. This one should prev top. Ooh. Okay. Then here, P should also have top. And then top. So since we called everything top, it sounds more like a stack now. Definitely more stack-like. Okay, so let's make sure everything works. Cool. Awesome. Great. Okay, so that's good. I think this is a basic linked list version of a stack. I think it's good enough. Kind of get the idea of what a stack is right now. I'd like to move on now to another data structure. Before we do that, let's commit. Okay. Boom, perfect. Okay. So let's talk about like what the advantages are with at least the stack, the two stacks that we made. So I'm going to create like a quick comparison here. So stack, and then we'll just say this implemented, let's say as an array. Actually, let's do it like this. Pros pros, cons. Then we'll say something like this. Then we'll have this. Extend that out here. Then we'll say this one is probably stopping nothing there. So I'll say array version. I'll say linked list version. Okay. So what are like the pros and cons of each approach? Well, the pros for, I guess, an array is no pointers. No pointers because we just had a max stack, like a max value. Another thing is so it's no pointers, so that's easy. What else? Cons is that since there's no pointers, our stack is fixed size. Okay. We have to keep track of index. Otherwise, we'll lose what is on top. Um, what else? Do we have a good fast insertion? Yes, we do. Fast pushing. Do we also have fast popping? Yes, fast popping. Because we're just accessing whatever that's on the top and just returning that value quickly. When we push, we just push it to the next available spot in our array in contiguous memory. So it's very fast. It's like constant time. So I'll just say that's like O1. Okay. Checking is empty is fairly simple. So I'll just say, okay, whatever. I think on both sides, fairly simple. So that's great. What else? I think overall it's a simple data structure. So really the whole advantage of a stack implemented as array is that it's easier to manage in that there's no pointers, and then pushing and popping things are very very easy. Okay. The downside here is that it's a fixed size uh, data structure. Since we are using an array, we had to allocate that array in the beginning, and so we're restricted to whatever size we make the array, and that's how many elements we can actually push into the stack. And then we kind of have to own the process and in terms of keeping track of where the top of the stack is in that array. So with the linked list, the pros is again the same. It's fast pushing, although not as fast as the array because we have to allocate stuff to the heap. We have to allocate nodes, and then basically um, there's like a little overhead rather than just placing data into memory directly. But we still get fast popping too. Same thing. There's a little bit more going on inside, but technically both are O1. The process stays more or less the same as your stack gets bigger. Um, Cons here. Oh, and here pros is that can grow as big as we need it to be, right? Because we since we're relying purely on pointers, heap allocations, we don't have like a fixed size for our stack. We can just keep creating nodes and chaining them together. The cons, though, is pointers. Pointers. Especially with the double pointer, depending on how you implement the stack. You have to manipulate a lot of this stuff, and we also had to keep track of the top of the stack too, just like the array. So the linked list one looks really good when you don't want to worry about having to hit a maximum limit for the stack, while the array is like it's simpler, but you're kind of limited to a specific size. So the next thing I want to kind of go over is that, okay, well, an array is a fixed size, but in other programming languages, that doesn't really seem to be the case. So like, let's talk about arrays. So in other languages, like for example, JavaScript, Python, you have like an array, but then you can have an array that can contain many different items up until, I don't know, n. And you don't have to define that. You can just push some sort of element into an array, and it will magically just insert that element into the array like this. Boom. So if I push again, the array starts to look like this. And magically, sometimes you just get the size of the array anytime you want. It feels like there's like no limit to the size of the array in these languages, right? Like you can just push as many elements as you want. You can get the length at any time, and you have all these crazy helper functions that can do so much on these arrays. You can slice, you can splice, you can, I don't know, you can do concat, put two arrays together. You can what else? You can zip, I think, zip through an array for Python. You do so many things, but these aren't really arrays. These are, what we call sort of array list like or dynamic arrays. So what they are is they are not fixed size and can grow as much as we need them to be. We need them to be. And also, what's really interesting is they provide a rich API to handle these dynamic collections. So I'm going to give an example again, finding out the length quickly, concat, slice, and so on. Okay. Now so that's in C, what do we have? We just have an array, fixed array. Fixed, or we call static array. I mean, you could do it in two ways. You could declare an array in the compile time way, where you have to know the size. Ahead of time. Or you could do it at runtime. So that pretty much calls malloc and then allocates heat space. But at runtime, we need to know the size, which makes sense because we need to know the size in order to call malloc successfully. But what if there's a balance? What if we can actually go back and actually approach number 2 differently? Can we create a dynamic array in C where we can push as many elements into the array as we want, index into them using normal indices while maintaining constant time or 1. This is very important because technically, if we just wanted number 1, we don't need a dynamic array. We can just use a linked list. Linked list allows you to just create a node and attach it at the end of the list or at the head of the list anytime you want. And that's constant time. But what a linked list doesn't allow us to do effectively is to index into them. Can we get the second element in some arbitrary size list? Can't really. You have to kind of traverse from the first then to the second. How about the 1000th element? You had to traverse through 1000 elements in that list in order to get to that 1000th element. So with this dynamic array, we get the sort of the benefits of what we could do with the linked list, where we can push as many elements as we want into this array. And also we can index into them using normal indices. So for example, x2, x1000, and we would still be able to get that element in constant time. We also can do things like pop, mean get the end of the array and kind of alter it. We can actually also do something like peek to not alter it. We can also, concat 2 of them. We can slice. We could do many things. But I think the most handy thing is sometimes we just want to get the length of the array. That's helpful, right? So these little things here make it very convenient, and it makes C so much more pleasant to use when it comes to arrays. But unfortunately, that's not built in, and so we're going to have to build it. So let's think about it. What would we need in an array that grows dynamically? Well, there are rules that we have to think about in how to handle that. But let's just talk about what are the basic functionalities that we currently get with an array. So with a current static array, we can set items through what? X at I equals Z. That's how we set items. Set items at index I. We could also get item at index. As simple as that. These two are the most basic operations we want. We can also initialize things in compile time to an array, but we can talk about that later. We can't really get the length of an array, especially in dynamic. We had to kind of know that ahead of time. We had to know the size of the array. So to get the size, length, or length, or maybe size of the array, we had to know ahead of time. Okay. So thinking about this is my last question for this is, can we actually add more items than what the length of the array is? We can't. What we're going to have to do is, in this situation where we have a static array, if we want to add items that exceed the length of the array, we actually have to create a new array that's bigger than the current array, and then copy over the elements one by one into this new array, then add this new item in, and then set that array, this new array, as the array you're working with. So for example, and that's the drawback of having a static array. So the drawback here is, suppose we have an array W with 3 elements, and the length is 3. And let's say we wanted to add 4 to that array. Well, since the length is 3, we're kind of hosed. We can't just add it in. That's going to cause a lot of issues. So we're going to actually have a new array, W underscore T, that has space. Let's say maybe 6 elements now. Okay. So then what we have to do is we have to copy over each element in, and finally add this element here, but yet we'll still have room for 2. So then if we want to add maybe 5 here, well, let's say here, then we could, forgot to say this, we had to assign then W as a new WT as a new W. So then we can just say, now if we want to add 5, we can just add 5, and we're still safe because length is 6. We add 6 too, and that'll still be safe because we still have space. It's not only again until we get to adding 7 that we have to do the same process again, where we may create a new array with 12 elements. We're going to have to copy over each one again. And we'll have room for more. Then you have to just reassign, and W is all of a sudden a big array again. Okay. So we do this process over and over again, and we're in a static array. And that's tedious if you were to write that code by hand all the time, because well, you can have a function that can do that for you. But then that's where we get into the territory of, why don't we actually have special data structure that does all of this for us, where we can set items, get items. We can also get the length. So that's just what this doesn't provide you dynamically. And we can also resize as necessary. Automatic, without us having to go, oh, I don't have any more room. I got to resize the array now. We'll just have it be smart and just like grow as needed to fit the new element inside the array. So then we could just be doing stuff like this, where we have an API, a very simple API, where let's say, you know, we have an array, let's say in the dynamic sense. Where we have W is going to be calling dynamic array with some initial size. I think I said 3 before. And we just do this w.push for w.push 5, w.push 6, w.push 7. And then we'll just print W and we'll get something like this easily. That's mind-blowing, right? Because we initialize this as 3, but yet when we printed this out, we are able to get 7 elements out. Because internally, whenever we push, this actually resized to 6. Then when we had pushed 7, this resized to 12 behind the scenes. So that's the approach. So I think to start out with, our dynamic array should have the following API. Push some element, set some element at some index. Actually, let's do it like this. At index I, and we'll just get some element, and then we can just print the array W. Okay? So 1, 2, 3, 4 things to think about. 4 things to think about of what our dynamic array can do. All right, next thing. Well, what does our dynamic array look like? Let's say we only want to work with integers for now. Okay? Well, we're going to need to have a collection of numbers. And we'll also need to keep track of current, size. Actually, let's say current length. We don't want to say size. Size is like the number of bytes. Length. And then we also, so, this could be something like, currently we have 3 elements, 4, 5, etc. Basically the end of our collection. Lastly, we need to keep track of the capacity, the total capacity capable. That's kind of redundant. Basically, the total capacity of what we can store. So there's a difference between this one and this one here. So let's go back to here. When we're talking about current length, well, we'll say this. When we push 4, we had resized to 6. So 6 is actually the capacity, and length here is now 4 after we had pushed 4. If we push 5, capacity is still 6, but length now becomes 5. There are 5 elements, but we are capable of holding 6. Then when we push 7, our length, or actually push 6, our capacity is still 6. Then we push 7, our capacity becomes 12, and we'll still have a length of 7 elements. It's important to keep track of the capacity because that's going to allow us to resize our collection behind the scenes transparently as we're pushing things into this dynamic array. So all this is actually going to be a struct. So some data structure, struct dynamic array, for example. So we can model that like this in code. Type def struct dynamic array. Then maybe have something called a pointer to an int called data, for example. So this is going to be a pointer to pointing to a block of memory. So let's just start drawing our memory again. I don't like how I can't draw so straight. Just do that again. Try my best. Okay. So we'll have a pointer to an int called int data, and that could be any arbitrary block of memory. And we'll just repoint that whenever we resize things. And then we also have an integer here called length, which is going to be the current length of the dynamic array. And finally, we have int capacity, just to keep things simple. So this will be a dynamic array of integers. So that's how we can actually model this dynamic array using this definition here of our struct. So thinking about it, if we were to allocate one of these, so let's say this, since we type def it, we can say dynamic array W. If we did this, just bear with me, and let's say we actually initialized it to, let's say, 3 elements, for example. Well, is it going to be 3 numbers here followed by the length and capacity? Not really. Not really at all. So let's look at our memory again. 200, 201, 202, 203. Actually, let's do this. Let's do it the right way. Let's start writing our memory addresses properly. So we'll have 200. And our struct is going to live here. We're going to have an int star data. Okay? And we're going to have room for whatever value this is going to be. This is starting at 200. Therefore, if this is a pointer to an int, which is basically a memory address, that's going to be 8 bytes. So that starts at 208. Just pretend. The struct will then have a length, just a normal integer. Okay? And then, since int is 4, this is no longer 0. This will be 212. And then we'll have capacity. So we're starting to do it the real way, I guess. Closer and closer. Now here, it's going to be 216. That doesn't really matter for this case. So let's say there's lots of memory addresses down here, and then now we have 400, just for ease. Then we'll have 404, 408, 412. What do you think this is? So let's say we initialize the capacity to be 3, and now the length starts out at 0. What is this? This is actually... Ooh, messed up. This is actually pointing to the base address of where our integers will begin. So this could be, A, B, C. We have 3 integers capable. We're allocating this much memory because our capacity is 3. This block of memory here is going to be allocated for this guy because we said capacity is 3. So we'll start at 400 here. And that's what our pointer is for. So then slowly, when we start to resize things, all we have to do is just update the memory address here to the location where our next block of memory is with a bigger size allocated. So that's the idea of where we're going to go with. Yeah, so I think that's enough for us to actually just start writing some boilerplate code. And then we'll probably leave it there for today. But that's the idea of a dynamic array. We just want to have an array that's going to grow as necessary. We're not going to be able to exactly access a dynamic array as we normally would with the square bracket notation like this. But we can certainly access our array elements using some API available to us. So getI is pretty close. It'll allow us to kind of index into it anyway. So let's do it. All right. So let's create a new project. Make their dynamic array. Okay. Did it show up here? Yeah, it did. I don't know why I keep clicking back. Silly. Okay, so again, our normal include stdio.h int main int argc character star v. Okay. We return 0. And let's begin. So the first thing we can do is we can type that a dynamic array type. So we type def dynamic array. Then we'll type def struct. Sorry. Type def struct dynamic array, and then we'll alias as dynamic array. So we'll have a pointer to an int called data. We'll also have length, and then we'll also have capacity. And let's comment. Let's say total size of which data can grow to. Total number of elements. Okay? And you know what? Let's do it like this. Let's make it cleaner and do it like this. And here, length will be the current number of elements of the array. Okay? And then data is going to be the block of heap memory containing the collection of ints. So pointer to an int. Okay? Pointer to an int. So that's our dynamic array. And let's just have like a simple I would say a simple function that can initialize our dynamic array and give it back to us. So we can have something like, for example, let's do this. Let's make it a void. And let's actually then take in a pointer to a dynamic array. So in this case, we'll say initialize. So let's say dynamic. How should we call this? Array. Array. Yeah, how about dir? Dir initialize. And then we'll say it gets a dynamic array pointer, cur, and then we'll say maybe int initial capacity. Okay. Now when we receive this pointer, we're going to have to then initialize it with the appropriate block of memory data and also the length and capacity of where this is. Now, when we initialize, going back to our memory map, we're passing in a pointer to the struct dynamic array. So going back to this memory thing here, we're not exactly passing in 200. Well, we're not passing in this whole thing, really, because that's just going to be a copy. So if we were to kind of extend this here, and let's just create some space. And now let's say here is 100. We'll pass in this dynamic array pointer called, what do we call it? Cur. That'll be 200. So we're passing this guy here, and we're going to dereference that and then actually start initializing things in here. So let's just make sure that works. When we pass this in, actually, we're going to pass two parameters into, let's say, a copy, because we're calling a function. Okay, we're calling a function, and we're going to say, well, this is going to be the same dynamic array, pointer to a dynamic array, because that's a copy. So that'll be 200. And then this will be the size, initial capacity, say init cap, would be 3. So this could be in main, and this will be our initialize. So then if we dereference it, we get back to the same spot. So that actually seems like it might work. It's not only until we want to modify things, like modify where this is pointed to, that's where we run into issues. Then we need that whole double pointer thing, I believe. So I'm just trying to make sure that we have our concepts right before I do anything. So I think the first thing that's easy is, well, let's dereference cur. Okay, let's get that value, and then let's set the capacity 3, or to initial capacity, sorry. Okay, remember, we can actually shorthand this now to this. We can also say the current length in this case is going to be 0 because it'll be empty. And we can then malloc this to be size of an int times the number of elements that we want total available. So that's just going to be the initial capacity. So that's the number of bytes we're going to allocate for data. Okay, so will this work? Well, how do we know if it works? Well, let's just start to hardcode things. So we'll have a dynamic array called W, for example. And let's just say we'll have data to be null. Then we'll also have dot length to be 0. Then we'll have dot capacity to be 0, just for example. And if we do die array initialize, we can pass in the pointer to the dynamic array, and we'll say initial capacity is 3. Next thing we want to do is after that call, let's print out that data. Just see what happens. So dynamic array information. So we want to know the number of elements. So the current number of elements, and the current number, the current size. So capacity. So we'll say length, capacity, new line, and then let's do w dot length, w dot capacity. Okay, going nice and slow. Nice and slow. Okay. We forgot to include stdlib. So let's do that because it couldn't find malloc. So include stdlib.h. Then we can compile. And then when we test it, we have initialized our dynamic array correctly. We can also check the size of the dynamic array. So size, or actually, how could we size in bytes? Okay, and then we could do, instead of this, we could do size of w.data and see what happens. What do we get back? We'll probably get a warning. Yep. Size in bytes, 8. Is that correct? Well, let's see. Let's think about it. What do we expect? 8. Let's think about that. Well, if you think about it, 8 is the address. So going back here, like I said before, this is actually only 8 bytes. Because this is pointer, we're doing the size of a pointer. Interesting. So no real way to do that, except we can say, well, what is the first element here? Can we dereference that? And actually go first element. And now, since we've already allocated this data here, let's just set the first element. So why not? So we can say star, or we can star w.data, like this, plus 0, the 0th element. Let's set that to 7. Let's see what happens if we dereference that. Dereference that first pointer. First element is 7. So our dynamic array works somewhat. But we have to be careful here in that this data here is going to be a pointer, a memory address. So whenever we modify or add elements, we're going to have to dereference that pointer, meaning we're going to follow the line here to that block of memory we assigned. Okay, so I think this is a good start to our dynamic array, and we can continue next time. Thank you.